Hello viewers, in today's session we are going to discuss another important and conceptual problem from Fourier transforms. And here in this class we are going to solve this problem where we are given a function that is f of x, and the Fourier sine transform of this function f of x is given as e raised to minus as divided by s, right? So here the Fourier sine transform of this function f of x is given as e raised to minus as over s, and we have to find out the function f of x. So for this we have to make use of the inverse Fourier sine transforms, right? And here we are going to use two important concepts to solve this problem. So now to find out this function f of x, we are going to use these two important concepts, right? So here we'll make use of this concept, that is the first one is differentiation under the integral sign. And when we apply the concept of differentiating an integral under the integral sign, will form a differential equation, and then we'll get a variable separable form of differential equation, and then we'll solve the differential equation, and we'll get the function f of x. And while solving this problem, we'll also make use of this standard result, that is integral 0 to infinity e raised to minus mx cos nx dx has this value, that is m divided by m square plus n square. So these two key concepts are going to be used to find out this function f of x. So now let us start with the definition of the infinite Fourier sine transform of the function f of x, right? So the infinite Fourier sine transform of f of x, where x is greater than 0, less than infinity, that is here we can write x belonging to the interval 0 to infinity, right? So the infinite Fourier sine transform of f of x is denoted by fs of s, and here we have capital F, here we write s, and here we have the function f of x. So in the usual notations, we have the infinite Fourier sine transform of the function f of x, that is given by this integral, that is 0 to infinity, and here we have f of x, and here we have sine s times x and dx, right? So in the usual notations, we can define the infinite Fourier sine transform of f of x in this way, right? And the inverse Fourier sine transform is given by here f of x, that is equal to f inverse, and here we write s, and here we have fs of s, and here we have the coefficient 2 over pi, and the integral 0 to infinity, and here we have fs of s, and sine s times x, here we have x, and here we have a ds, right? So this is the definition of infinite Fourier sine transform of the function f of x, and this is the definition of inverse Fourier sine transform of f of x. So here we are going to use this definition because we have to find f of x, because its Fourier sine transform is given as e raised to minus as over s. So now here we are given the Fourier sine transform, that is fs of s as e raised to minus as over s, right? So let us substitute this value in this integral. So now we can write here f of x is equal to 2 over pi, and we have 0 to infinity, and for fs of s we have e raised to minus as over s, and here we have sine s times x and ds, right? So now we have the function f of x, which can be expressed in this way, right? So now we'll make use of this concept, that is a differentiation under the integral sign. So what we will do, we'll differentiate both sides with respect to x, right? So we have here d by dx of f of x, and here we have 2 over pi, and here we have 0 to infinity, and here we have the derivative of this function, because we have to differentiate this function with respect to x, right? And here we have s and x. So we'll treat s as a constant, that is we'll calculate the partial derivative of this function with respect to x, right? So here we have e raised to minus as over s, and here we can write del over del x, and here we have sine s times x, and here we have ds. So now we have d by dx of f of x, and this is 2 over pi. This is 0 to infinity e raised to minus uh, as over s. Now the derivative of sine s times x with respect to x is cosine s x, that is s times x, and here by using chain rule, the derivative, that is del by del x of s times x, keeping s as a constant, we have s, and here we have del over del x of x, that is s times 1, that is equal to s. So here we have s, and here we have ds, right? So now s and s get cancelled, so we can now write d by dx of f of x is equal to 2 over pi, and here we have 0 to infinity, and here we can now write e raised to minus as and cos s times x, and here we have ds, right? So using this concept, that is differentiation under the integral sign, we have now this expression. So now we can write the value of this integral by directly using this result, right? So here we have 0 to infinity, and the integrand is of this form. So here we have e raised to minus as and cosine s times x, and if we compare this integral with this one, then the value of m is given by a, and the value of n is given by x. So now using this result, we can now write dy dx of f of x, and here we have 2 over pi, and here we have m divided by m square plus n square, so m is a. So we have here a divided by, here we have a square plus x square, right? So now we have a differential equation, right? So here we have formed a differential equation using this concept, and we can easily see that this differential equation is of the variable separable form, right? So we can now write here d by dx of f of x as f prime of x, right? So we have f prime of x is equal to 2a over pi, and here we have 1 over a square plus x square. So we have here d by dx of f of x. So now separating the variables. So here we have f of x, that is d f of x, and here we have a 2a over pi, and here we have dx over a square plus x square. So now integrating both sides, here we have c as the constant of integration. So now here we can simply write f of x, and here we have 2a over pi, and we have dx over x square plus a square, and c is the constant of integration. Now here we can use a standard result from indefinite integrals, that is integral. So we have here a dx over x square plus a square is equal to 1 over a tan inverse x over a. So this is the standard result. So here we have f of x equal to 2a over pi, and here we have 1 over a tan inverse x over a plus c, where c is the constant of integration. So here a and a get cancelled, so we have f of x is equal to 2 over pi, and here we have tan inverse x over a plus c, right? So our function f of x, now it takes this form, and here now we need to find out the value of this constant of integration c. So now to get the value of c, let us take x is equal to 0 in this expression. So we have now f of 0 is equal to 2 over pi tan inverse 0 over a plus c. So we have f of 0 is equal to 2 over pi. Tan inverse 0 over a is simply a tan inverse 0 plus c, and here we have 2 over pi, and the value of tan inverse 0 is 0, and here we have c, so this is 0 plus c, that is equal to c. So the value of f of 0 is equal to the constant of integration c. Now to get the value of f of 0, let us substitute x is equal to 0 in this expression. So here we have f of 0, and we have 2 over pi 0 to infinity, and we have here sine s times x. So when we take x is equal to 0, then this term is 0. So sine 0 is equal to 0, and here we have a ds. So this entire term it reduces to 0. So f of 0 is equal to 0, and f of 0 is equal to c. So therefore by these two expressions, the value of the constant of integration c as equal to 0. So now let us substitute this value of c in this expression. So our function f of x is now equal to 2 over pi tan inverse x over a plus 0. That is f of x is equal to 2 over pi tan inverse x over a. So this is the required expression for the function f of x, whose Fourier sine transform is given as e raised to minus as over s, right? So viewers, this is how we can find out the function f of x if its Fourier sine transform is given as this expression.